Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we will be discussing Chapter 5.1.5, which is Completing the Quadratic Web. This chapter basically culminates everything that we know about factoring, about x-intercepts, about zero product property, and it culminates it into basically how do we write the equation of a quadratic and how does all of the factoring play a role. And so in the first problem here, it says several parabolas and equations are shown below. Match each equation with its graph, and then justify your choices and any shortcuts you discover with your teammates. So you're supposed to work on this as a team, but of course, if you're watching this at home, then that would be quite impossible. But let's go and take a look at number one here. First off, notice how there's 6 graphs and there's 9 equations, which means not everyone's going to be matching, and I think they already told me that. I didn't need to explain that. That's fine. Okay, so let's go ahead and take a look at number one here. Number one has x-intercepts, right? It has x-intercepts at -7 and 4. So if I say this is at minimum an x plus 7 times x minus 4, and again, how did I get that? It's because I did that whole reverse engineering thing where x equaled -7, so my factor was x plus 7, x equaled 4, so my reverse engineering factor would be x minus 4. If I multiply this guy out, I'm going to get x squared minus 4x plus 7x minus 28. And if I combine my like terms, I'll get x squared plus 3x minus 28. And I believe that is one of the answers. I believe this is B. And so number 2 is going to be kind of the same thing. So I'm going to go ahead and do y equals. And again, I'll go and just write out the factors because I think we've been through this practice enough to where I can bypass all of the -6 comma 0 is the x-intercept, therefore the 0 is x equals -6, therefore the factor is x plus 6. And I know I just did it, but to say that it wasn't necessary, but I'll just do it again. So x plus 4 here. Hopefully, again, you guys know where I got that from. Let's go ahead and multiply this guy out. So x squared plus 4x plus 6x plus 24. So y equals x squared plus 10x plus 24. Do we have a winner? E, I believe, is the one you are looking for. And then number 3, notice how it only has one value. Now, when we first started looking at quadratic equations and their graphs, one of the things we noticed was that whenever you had a perfect square trinomial, the quadratic would bounce off of the x-axis at the place where the factor would equal 0. And so since this is -3 comma 0, right, it has to be A or H. And so between the two, -3 will not make H 0, right? It will make it'll make -6 in here, which will give you -36. So I don't think H is going to be our character. I think that A will be. Because if I, again, imagine myself plugging in a -3 into the x plus 3 squared, I will get 0, which is going to be my x-intercept right there. And so I believe 3 is going to be none other than A. This one here, 0, 0, and 4 comma 0, again, it's the same idea, right? So x, let's say -0 times x minus 4. I can go and shorten him up to call him just regular old x. And that will make the distribution a lot easier. So y equals x squared, oops, not plus, but minus 4x. And is that in there? It's G. Good job. 5. It's the only upside down one, right? So if you look at all of these, what is the characteristic of the upside down parabola? Well, it's got to be D. There's a negative in front of that x squared. Another thing about it, we talked about this in the very first time we talked about graphing quadratics, was that when there's no linear term, notice how there's no like plus 3x or plus 7x in the middle. This thing is centered at 0, positive 4 rather, 0, 4. And notice how that's what happens when you let x become 0. You straight up get 4. And so whenever you have this binomial expression going on, if the other term doesn't have an x, it's a pretty good bet 0 is going to be the coordinate of your vertex, or the x coordinate of the vertex anyway. This guy here, little more difficult here because there's some fractions involved, but that's okay. I can once again call this x plus 1/2 times x minus 3/2. So what I'm going to do is I'm going to go ahead and multiply this guy out. So y equals. So I've got x squared minus 3/2 x plus 1 half x minus, now I'm going to go ahead and multiply this thing together, and I get negative 3 over 4. So these guys together will become x squared minus negative 3 halves plus 1 half is negative 2 halves, which is negative x, and then minus 3/4 is equal to y. Now, nothing in here matches that, but notice how there's a denominator of 4 here. If I wanted to get rid of him, I could just upscale everything by 4 and call it y equals 4x squared minus 4x minus 3, and that would make this letter I. So again, we're going back to that whole writing the equation of a parabola, and yeah, and this time they just gave us graphs instead of a table like they did in the last lesson. But as long as we have those x-intercepts, I want to keep on reinforcing that. As long as we have those x-intercepts, we will be fine. And as long as we have a third point, then we can solve for that a value. But we're just matching here, so we're good on that. I'll be back with the next problem. For this quality control problem, they're telling us to read the complaints of the parabolas and then write a friendly response that offers a solution to the problem. And so basically, we just have to write the equation of each parabola given those conditions. And so in letter A, they're talking about the person in Pennsylvania. They're saying that they followed all the instructions and they ordered a parabola that passed through the points, and it seems like you sent the wrong one. Please tell me how to order the correct parabola. Your immediate reply is appreciated. So right now, it looks like this dude has a problem here, this Pennsylvania person. So this person doesn't have enough information to order the correct parabola because we need a third point. And so I would just write that down. I would say this quadratic is not yet clear on its parameters. It needs a third point in order to determine which way it is facing, as well as the stretch factor. So that would be it. We can't send this dude a new parabola because he hasn't told us the parameters yet. So sorry, dude. It looks like you're kind of up the creek, but that's not my problem. Let's see. So from here, the next one in B, it says, "Dear Miss Quadratic, I'm very disappointed. I want a parabola that hits the x-axis only once, and yet I see no mention of this type of parabola in your pamphlet. How should I order my special parabola?" So if they want a parabola that only hits the x-axis once, we've been through this before, where we want them to order a perfect square trinomial. Now, a perfect square trinomial, an example of this would be something like y equals x squared minus 6x plus 9. Because we know that this thing factors into x minus 3 times x minus 3, or more to the point, x minus 3 squared. And I know I said I didn't really care about consolidating this, but now would be a good time to start learning how to consolidate it, because now the ability for us to do that will allow us to service this troubled in Texas person much more easily. So because they want a parabola only to cross once at 5, 0, what we want is we want a version of this that is y equals x minus 5 squared. Now, they don't specify whether or not they want it to be an upward facing or a downward facing parabola. So at this point, I would say this would be the baseline function for them. And I would say that, I would say this will serve as a baseline function for your needs. But please specify if you want it upward or downward facing, as well as any stretch factor. But that should get them by at least on what they want for the 5, 0 intersection. And so, but yeah, the rest of that's going to have to be up to them. In part C, it says, "Please help. I have searched through your entire brochure and do not see a parabola that fits my needs. All I want is a parabola that looks like this." Okay. And they want a parabola that looks like that. So let's go ahead and get some intercepts here in part C. I'm guessing that crosses at negative 3, 0 and at 2, 0. And here we are. We've done this many times before. This is x plus 3. I'll go and fast forward that. This is x minus 2. I'll fast forward the whole reverse engineering in detail. So what I have is y equals a parentheses x plus 3 times x minus 2. And now I'm going to go and choose that third point. The third point would be a really good, a really clear selection would be the y-intercept, which would be 0, 6. So I'll say 6 equals a times 0 plus 3 times 0 minus 2. A times negative 6 equals 6. Again, we're just multiplying. Divide by negative 6 is a equals negative 1. So that means that what you have is you have y equals the negative version of x plus 3 times x minus 2. And we'll go and multiply that out. X squared minus 2x plus 3x minus 6. It's all being negative. So negative x squared plus x minus 6. And you can go and leave it like that if you wanted to, or you could distribute the negative and get negative x squared minus x plus 6. Either one would be acceptable. So there goes that quality control. I think the C person kind of knows what they want, but they'll have to, Pennsylvania and Texas, they'll have to tell me what they want more specifically in order to get the parabola that they want. All right, I'll be back with the next problem. All right, now we are back to the water balloon toss of a couple sections ago. Now, what they want us to do, now that we have the skills to write the equations of parabolas, they want us to write the equations of parabolas for everyone except for Mags, because Mags actually did have her parabola in working order. So in part A, we're going to examine Jen's graph here. We know that the x-intercepts are going to be at 0, 0, and at 8, 0. So they want us to write the equation for this. And so I know that this is going to be, x minus 0 as my factor and x minus 8 as my factor. Now from here, I'm going to go ahead and say that my equation is going to be y equals a parentheses x minus 0 times, actually I'm not going to do x minus 0, I'll just do x times x minus 8. Now that third point, usually we choose the y-intercept, but this time I'll go and choose the vertex. The vertex, I believe, was at 4, 32. So my third point will be at 4, 32. And so I'll go and throw those things in. So 32 equals a times 4 times 4 minus 8. So that's a times, so this is going to be negative 4 here. So a times negative 16 equals 32. So dividing both by negative 16, a will equal negative 2. So what I've got is y equals negative 2x parentheses x minus 8. And that might be fine, but if you wanted to distribute, you would do negative 2x squared plus 16x. Again, with these water balloon problems here, please expect your a value to always be negative because we are launching the balloon in the air and then it lands on the ground, so it's an upside down parabola every single time. If you don't end up with a negative a value, you've probably done something kind of wrong. In B, we're talking about altruistic, and it says he releases the balloon from the 10-yard line and it lands at the 16-yard line. So what does that tell us? Well, it means that we have an x-intercept of 10, 0, and another one of 16, 0. And his balloon reaches a height of 27 yards. And so we know that his vertex is blank, 27. So remember, the vertex is always smack in the middle of the x-intercepts. And so with this guy being 10 and this guy being 16, hopefully it makes sense that your x-coordinate of your vertex would be 13. So now we're back in Jen's position. So we're going to say y equals x minus 10 times x minus 16. Don't forget the a. So now I'll go and say 27 equals a parentheses 13 minus 10 times 13 minus 16. So that's going to be a 3. That's going to be a negative 3. So negative 9a equals 27. So dividing both by negative 9, a equals negative 3. So what I've got is I've got y equals negative 3, parentheses, x minus 10 times x minus 16. Let's go and multiply that out. X squared minus 16x minus 10x plus 160. So then let's go and go x squared minus 26x plus 160. And we'll multiply that all by a negative 3. So y equals negative 3x squared. That's an equal sign. Plus, let's see, 26 times 3, 78. So plus 78x minus 480. And there you go. There goes Al's equation. So I'm sorry I'm kind of speeding through a little bit, but I'm pretty sure you're kind of seeing how this thing works here. The journalist knows that the factored form of a quadratic equation or quadratic function is y equals a parentheses x minus d times x minus f. Explain to the journalist how she can determine the values of a, d, and f to write the equation of a quadratic function in factored form. Give examples. Okay. So from here, the d value and the f value will always be the opposites of the x-intercepts, right? And so from here, let's go ahead and say y equals a parentheses x minus d times x minus f. So we can say that d and f are the x-intercept values. And a is the stretch factor. So for example, if I do y equals negative 4, parentheses, x plus 1 times x minus 7, here's an example that they're asking for. We know that my x-intercepts are going to be at negative 1, 0, again, the opposite of that positive 1, and 7, 0. And my stretch factor will be 4, and the negative means it's also going to be upside down, or downward facing. So there you have it on completing the quadratic web. We are knee deep now in writing equations of quadratics based on graphs, based on tables, and we are seeing how factoring affects quadratic functions as well. As always, please leave comments or questions in the comments area, and I will see you all in the next episode.